welcome back to our new session. Now, in this session we will be talking about application of Bernoulli's equation to various engineering devices. But before we go and do that, I will talk about a few basic concepts which will help you understand what I will cover next. So, we will look at now concepts of stagnation pressure, dynamic pressure, and static pressure. Now, first of all, I will talk about what is called a stagnation point. So, this is a point where the velocity is 0. Now, I will take an example and show you how to find the stagnation points. So, let us say the velocity field is denoted by ui plus vj for a 2-dimensional flow. So, this is an example of a 2D flow where w component of velocity or the z component of velocity is 0 and u is not a function of z. So, u could be in general a function of x and y, v could also be a function of x and y. So, I will take an example where u is x and v is minus y. Now, we will find the streamlines of the flow. So, we will start with the definition of a streamline. So, this is a 2D flow. So, if I show the coordinate system x y, this is the origin. Suppose you have a curve. If this curve is streamline, then the tangent at every point on the curve will be in the direction of the velocity vector. So, if I look at this particular point, the velocity vector will be in this direction. Now, suppose I say the equation of the curve is y is a function of x, then the slope of the curve dy dx you know is tan of this angle. So, if I call this angle theta, it is equal to tan of theta. Now, if this is the velocity vector v, it has a component in the x direction which you are calling u and the component in the y direction which you are calling v. So, this will be your u and this will be your v. So, you can see that tan theta is also equal to v upon u. So, this is the equation of the streamline in 2D. So, this equation you may also write in the form dx by u is dy by v. So, in our example we have taken a simple example, and this is a example of a flow which does which is seen in practice. If I say u is x and v is minus y, this is the example which I took, then dy dx is v by u, which is minus y upon x in this example. Now, this is a differential equation which can be easily solved. I can write this as dy by y is equal to minus dx by x. So, you see that the left hand side is a function of y into dy, the right hand side is a function of x into dx. So, we can get an analytical solution easily. Now, suppose I integrate this, then you will have dy by y is minus integral dx by x. So, this will be natural log of y and the right hand side will be minus natural log of x, and there will be an arbitrary constant of integration. Now, I can take this term and bring it to the left hand side and write this as log of y plus log of x is equal to c, or I can also write it as log of x y is equal to a constant, because you know that log of x y is log of x plus log of y. Now, if log of x y is a constant, that means x y is a constant. So, equation of streamline is of the form for this particular flow x y equal to constant. Now, let us say I want the equation of the streamline through a particular point. So, I will draw the coordinate system here. This is a this is the origin, this is x and this is y. Now, let us say I take a point here. What is the equation of the streamline through this point? Well, it will be x. If I say this is a point P, then x y will be equal to x p into y p. Now, if I draw the streamline, it will be a rectangular hyperbola like this. Now, if I draw the tangent here, it will be in the direction of the velocity. We have seen that you are given that u is x. So, u p will be x p, which is positive. Now, v p is minus y p, and for this particular point which is in the first quadrant, y p is positive. So, this will be negative. So, you have a positive x component and a negative y component. Now, suppose I take a point q which is a mirror image of this point p about the line o y. So, suppose I have a mirror here and call this a point q. Now, since it is a point in the second quadrant, x q is positive and y q is negative. So, if you look at u at the point q, it is x q which is negative, and if you look at v at the point q, that is minus y q. Now, y q is still positive, so and there is a negative sign. So, this is negative. So, the streamline through this will be like this. So, if I draw the tangent here, this is the direction of the velocity. It has a negative y component as well as a negative x component. Now, we will consider a point A over here. What is the equation of the streamline through this? Well, it will be x y equal to x a into y a. So, that is x a, and I have taken a point where y a is 0. So, this is equal to 0. Now, I can take a point B over here, then x y will be x b y b, and again that will be 0, because here x b is 0. Now, you see that x equal to 0 is a streamline. So, this line is a streamline, and this line is also a streamline, and these two streamlines are intersecting at the origin in this example. So, I will draw that figure again. This is the origin, this is x, this is y. Now, equation of streamline through O, the origin, is again x y equal to 0. So, here you have two separate lines actually. This is the line y equal to 0 and this is the line x equal to 0. Okay. Now, two streamlines can meet at a point only if the velocity is 0, otherwise you will have two tangents. So, here what is happening is, if you look at dy dx, that is v by u. Now, v is u is x. So, u is 0 at the point O and v is minus y, which is also 0 at the point O. So, here what you have is a form indeterminate form 0 by 0. So, you can take the limit and you may get two values depending on whether you are approaching the point O along this line or whether you are approaching it from this line. So, this point where the velocity is 0 and where the streamlines are intersecting, it is called the stagnation point. So, O is a stagnation point. So, here u at O is 0, v at O is 0 and w at O is also 0, because we have taken a 2D flow, and you can see two streamlines are intersecting. Now, let us consider a flow, inviscid flow over a solid impermeable wall. Suppose this is the wall and I have x along this and y along this. Now, I can take a small area element here dA. We will consider as another example a porous wall, which I will indicate by dotted lines. এখন কেউ দেখতে পাচ্ছে না? Now, if I take a area element dA here, you can have a flow through this. So, this is a porous wall and this is the impermeable wall. So, if it is impermeable, you can take any area element on the wall and the volume flow rate or mass flow rate crossing it is going to be 0, and that can happen in continuum mechanics only if the normal component of velocity is 0. In this case, the y component of velocity. Now, if it is an inviscid flow, it can slip along the wall. So, you can have a velocity vectors with arrows like as shown over here. The fluid is going to be tangent to this and the normal component of velocity is 0. So, for an impermeable wall in inviscid flow, this is going to be a streamline. So, any solid surface placed in an inviscid flow will be a stream surface. Now, let us look at a familiar example. flow over a cylinder in cross flow. So, you have a solid cylinder in the form of a circle, and I can have x this way, y this way, the origin, and let us say upstream you have a uniform flow with some velocity u infinity, and let us say the corresponding pressure is P infinity. Now, if you look at the streamlines upstream, they are going to be all parallel to the x axis. So, these are the upstream streamlines. I can show the arrows to indicate the direction of flows, and this wall also is a streamline because the solid surface. Now, if you do a flow visualization, you will see that you will have one streamline which comes horizontally and hits this point here, and quite often the flow pattern may be steady and symmetric, and you will have a streamline this way, and the other streamlines will become curved and go over this. Now, of course, the flow pattern for viscous flow will depend on the value of the Reynolds number, and you have different flow patterns, but if you have inviscid flow, which we will discuss in greater detail towards the end of this course, you will have a pattern like this. Now, the reason I brought up this example is to show you the practical utility of what we are talking about. So, here you have a case where this point, at this point two streamlines are meeting. One is this curved streamline, which is the surface of the cylinder, and one is this horizontal streamline over here. So, there are two tangents. If I draw the tangent to this, is at right angles to this angle is 90. So, this point will be a stagnation point where the velocity is 0 even in inviscid flow. At other points along the surface, the velocity will not be 0. So, this is what we will call the forward stagnation point. I am denoting by Fs, and similarly here you will have another stagnation point which we will call the rear stagnation point. I am indicating that by the Rs. Now, if you look at the fluid flow, fluid will flow tangentially along this because it is inviscid flow. We will show later that the maximum velocity will occur at the top and at the bottom. The flow pattern is symmetric, but at this point the velocity will be 0. Now, so these are two stagnation points. The pressure at these points are called stagnation pressure. Now, suppose I apply Bernoulli's equation, say between a point 1 over here and this point which I call 2, then you are going to have P 1 plus half rho V 1 squared plus rho g z 1, sorry, this will be now y 1, because if I take it to be a horizontal cylinder with g downwards, equal to P 2 plus half rho V 2 squared plus rho g y 2. Now, if it is a horizontal cylinder, then y 1 will be equal to y 2. So, these two terms will cancel out. So, there is no change in the potential energy, and since 2 is a stagnation point, this value is 0. So, P 2 is what you call the stagnation pressure. So, this is equal to P 1 plus half rho V 1 square. Now, P 1 is nothing but the upstream pressure P infinity, and V 1 is nothing but the upstream velocity u infinity. So, what you are going to have here is that the stagnation pressure will be P plus half P infinity plus half rho u infinity squared, and of course, we have taken an inviscid fluid with constant density rho. Now, rho v squared has the units of velocity, and since it is associated with velocity, this term is sometimes referred to as dynamic pressure. and P stag is the stagnation pressure. Now, to distinguish this P from what we are calling stagnation pressure, we sometimes refer to this as static pressure. So, the stagnation pressure is the sum of the static pressure and the dynamic pressure for inviscid flow with constant density. And so, this static pressure is nothing but what we were earlier calling pressure P. Here, to emphasize that it is different from stagnation pressure, we have added this term static. Okay, we have been told that there is a network problem, so we will take a short break to rectify that. Sorry for the interruption, we had a network problem, so we had to take a short break. Now, I will give you a formal definition of stagnation pressure. এটা আসছে না তো আমরা দেখতে পাবো না। So, this is the pressure that the fluid will attain if it is brought to rest by an isentropic process. This is the formal definition of stagnation pressure, which also holds for compressible fluids. Now, we are dealing with a inviscid fluid. So, here the viscosity is 0 and all processes are reversible processes. So, automatically this isentropic process is going to be, this condition of isentropic process is going to be satisfied. And if you say it is a constant density fluid, that is rho is constant, so this is an example of an incompressible fluid, or if you neglect density changes, sometimes you can also call it an incompressible flow. Then for this case the stagnation pressure is, as we have shown, the sum of the static pressure and the dynamic pressure. So, this is the pressure we were talking about earlier, static pressure, and this is what you call the dynamic pressure. So, I will make a summary of the discussion which we just had. Two streamlines can intersect at a point only if v, the velocity vector, is 0 at that point. Otherwise, you have a contradiction in the sense that there will be two tangents to the curve. But I have taken an example and shown you that when the velocity is 0, if you take the limit, the limit depends on the direction in which you approach the point, and you could have two values of the slope. And if two streamlines intersect, the velocity is 0. So, whenever streamlines intersect, the point is what is called a stagnation point, a point where streamlines intersect is a stagnation point. So, if somebody shows you the streamline pattern either by solving the equations of motion, maybe using a numerical method, or by doing flow visualization, if you see that streamlines are intersecting at a particular point, you know the velocity at that point must be 0. And in inviscid flow, the pressure at a stagnation point in inviscid flow is the stagnation pressure. So, if you can measure the pressure at a stagnation point, you have the stagnation pressure, and there are certain situations where the stagnation pressure does not vary from point to point. So, you get the stagnation pressure at all points if you can locate the stagnation pressure stagnation point and measure the pressure at that particular point. Now, let us see how this helps us in measurements. Let us consider flow through a duct, inviscid flow, which is in this direction. Now, suppose I insert a tube or a body here, a slender body, but I am drawing an exaggerated view with a sharp nose. Then you will see streamlines coming here and then moving along this. So, this point will be a stagnation point. Now, let us consider a situation where I will draw another figure. You have a tube like this, and I drill a hole and put a pipe or tube in the center. So, the fluid is approaching in this direction, and if it is an inviscid flow, the velocity vectors will be like this, all parallel maybe. So, if this tube is aligned with the direction of the flow and I connect this to a U2 manometer, the reading will be the stagnation pressure at this particular point. Now, if you want to measure static pressure, if you consider this case where I drill a hole in the wall, and I can connect this tube to a U2 manometer and measure the pressure, the reading will be the static pressure at this point. So, when the fluid is flowing this way, and if it is an inviscid flow, you know that it can slip along the wall. The pressure read by this tube will be the static pressure, whereas the pressure read by this tube will be the stagnation pressure. So, this tube is aligned with the direction of flow and in the opposite direction. So, the fluid particles which are coming along this, they are brought to rest. So, the fluid which is inside this tube is entirely at rest. So, this principle we can use in what is called a pitot tube. So, you have a tube which has to be aligned with the direction of the flow, and if you are considering say flow over a wall, so this is a wall, and let us say this is the direction of the flow which is over the wall. Now, if I drill a hole in the wall of the solid wall and connect it to this tube using a U2 manometer, you you will find that if you have a manometer liquid here, the level here will be lower than the level here. So, this is your manometer liquid, let us say, with density rho m. Now, in the lab what you can do is measure this manometer deflection, which we will call H m. So, the subscript m refers to the manometer, and the density of the liquid or gas, whatever it is, which is at low speeds, which is flowing over the wall, we will denote by rho. Now, if you consider this particular streamline, if the tube is aligned with the direction of the flow, the streamline will come like this, and the fluid which is inside the tube will be at rest. This manometer liquid will also be at rest, and so, as well as this column of fluid. So, there are two fluids, one is the fluid which is flowing over the wall, and the other is the manometer fluid. Now, let us say there is an inviscid flow, and we will apply Bernoulli's equation between this point, which we will call 1, and this point, which we will call 2. Now, we will take a datum, and suppose I call this vertical coordinate z. Earlier I was calling it y, but you may be more familiar with this terminology, and the gravity vector is in the negative z direction, let us say. Now, if you apply Bernoulli's equation between 1 and 2, we know that P 1 plus half rho V 1 squared plus rho g z 1 will be equal to P 2 plus half rho V 2 squared plus rho g z 2. So, here I have assumed that rho is constant, the density is constant, and it is inviscid fluid. So, the viscosity mu is 0, and we are applying it for steady flow along a streamline between 2 points 1 and 2. Now, as you can see from this figure, the height, vertical height of points A 1 and 2 above this datum are the same. So, z 1 equal to z 2. So, these two terms will cancel out. So, there is no change in potential energy, and the velocity at point 2 is 0. So, V 2 is 0. So, P 2 is the stagnation pressure, because 2 is the stagnation point, and since rho is positive, V 1 square is positive, you can see that P 2 is going to be larger than P 1. That is why the liquid in this tube, manometer liquid, is going to be pushed downwards. Now, our goal is to find what is the velocity, let us say. So, if you can measure the pressure difference between the points 1 and 2, you get an equation for the velocity. So, from here half rho V 1 squared is P 2 minus P 1. So, the left hand side of this equation is the dynamic pressure, the right hand side is the difference between the stagnation pressure and the static pressure. So, V 1 squared will be 2 upon rho P 2 minus P 1. So, the velocity V 1 is under root 2 by rho P 2 minus P 1. So, if you can find this difference P 2 by minus P 1 using this manometer, and if you know the density of the fluid which is flowing over the wall, you can find the velocity at this particular point. Now, let us see how to find the difference in the pressures. Now, this column of fluid is at rest. So, we can apply the equations of hydrostatics here, but the fluid above the wall, it is not at rest, it is flowing over the wall, but in this particular flow the streamlines are parallel to the wall because it is inviscid flow, and they are straight lines. So, the radius of curvature is infinite, or in other words the curvature is 0. So, the variation of pressure in the vertical direction, although the fluid is flowing horizontally and not at rest, is still going to be given by your hydrostatic equations. So, the pressure will increase linearly as we move downwards in the vertical direction. So, let me draw that figure again and show you how to find the pressure difference. So, this tube, this is your pitot tube, and this is a wall over which the fluid is flowing. This is the static pressure tap on the wall, and we have connected a tube to the static pressure tap, which is bent like this. It is a flexible tube and connected to this pitot tube. So, this is the manometer level. Now, we were considering flow along a streamline, and this point we had called 1, this point we had called 2. Now, if you go along and this point you can call 3, this point you can call 4, this point you can call 5, this point you can call 6. So, these are the streamlines of the flow. Now, in the lab what you have measured is the difference in height between the 0.6 and 5 or the 0.6 and 4, whatever you want to call it. So, this is the manometer deflection, which I am denoting by the symbol small h with a subscript m, and the density of the fluid in the manometer I am calling rho m. Now, what we wanted was the difference in the pressure between 1 and 2. Now, I can see that P2 will be equal to P3, because the fluid is at rest in this tube. And this is a horizontal tube. Now, if you look at the pressure at 4, let us say, this column of liquid is at rest. So, P5 and P4 will be the same, and P5 is P6 plus this. So, if you look at P6, that is going to be equal to P1 plus rho g times, if I denote this length by L, it will be P1 plus rho g L. Now, if you look at P5, that will be P6 plus rho m g h m, which is the same as P1 plus rho g L plus rho m g h m. Now, we know that P5 is equal to P4, because these 2 points are connected by a fluid of constant density. This fluid is at rest, and 5 and 4 are at the same horizontal level. Now, P4 we can say is P3, the pressure at this point, plus rho g L plus h m, because the difference in height between points 3 and 4 is the sum of L and h m, and P3 is P2. So, this is P2 plus rho g L plus h m. Now, P5 is equal to P4, which has given you this, and P2 is the same as. So, from this equation, if we have already found P1, so I will write it here or below. Instead of P5, I am writing this equation P1 plus rho g L plus rho m g h m. So, this whole expression is P5, which I have got from here. So, this will be equal to P 4 as I have written over here, which you can write as P 2 P 2 plus rho g L plus H m. Now, you will notice that this rho g L and this rho g L will cancel out, and you have rho m g H m and rho g H m over here. So, this g H m is common to this term and this term. So, from here due to lack of space I have to write here on top, if you want P 2 minus P 1, I can bring this term to the left and right hand side over here and move this term over there. You are going to see this is equal to rho m minus rho into g into H m. So, I will put this in a box. So, this relation I have got from the last equation which I wrote over here. So, we know what is H m, this you can measure using a scale in the lab. If you know rho m and rho and g is the gravitational acceleration, then you can find what is P 2 minus P 1, and you can go back and substitute it a network problem is over here. Okay. So, now this instead of P 2 minus P 1 here we can write the relation. So, V 1 will be under root of 2 upon rho, and here you will have rho m minus rho g H m. So, we have got this expression finally. V 1 is under root of 2 upon rho m minus rho g H m, which you can express in this manner under root 2 g H m into rho m upon rho minus 1. Now, we will consider two examples. Say example 1, the fluid is say water and the manometer fluid is mercury. So, rho m is say rho of mercury and rho is say rho of water. Then you know that rho m by rho is the relative density of mercury or the specific gravity, which is 13.6. Now, we will take another example. Let us say rho m could be rho a g, or it could be rho of water, whatever it is, but rho is say rho of air. So, let us say this is water for simplicity. Now, rho m by rho is going to be the rho of water by rho of air. So, this will be the order of 1000 kg per meter cubed, and this is of the order of 1, or you can say 1.2, whatever it is, kg per meter cube. So, now this ratio over here is about 1000, and you can neglect 1 in comparison to this. So, quite often this can be approximated by, some people use this formula, root of 2 g H m rho m by rho, but this you should use only if the fluid is a gas and the manometer fluid is a liquid. Only then rho m by rho will be much greater than 1. So, in example 1 I have considered a case where the fluid is mercury, fluid is water and the manometer fluid is mercury, and if you neglect this 1, then you have a large error, because this ratio is only 13.6, not 1000, and if you neglect 1 in comparison with 13.6, you may have a 10% error. So, we have to be careful, and the best thing is to use this whole expression over here. where you have the difference in the density of the manometer liquid and the fluid whose velocity you are measuring. Now, we will consider the principle of a venturimeter. So, this venturimeter is a converging diverging duct which is inserted in a tube. So, let us say you have a want to measure flow in a pipe and you cut a section of the pipe and insert the venturimeter. So, this will be a converging section, this is the direction of flow. So, with respect to the direction of flow, this is a converging section, and then it will have a diverging section, and this is your pipeline. So, you can say that this device is the venturimeter, and you had this diameter here. So, if it is a pipe, then I will have to show the center line. This diameter, if it is d, then this diameter will also be d. So, this was your original pipeline, and what you have done is inserted this converging diverging duct in, which is called the venturimeter. Now, this point of minimum section here is what is called referred to as the throat of the venturimeter, and this is the converging section where the area is decreasing, area of the tube is decreasing in the direction of flow. And this part is the diverging section. Now, what we do here is we will drill a hole here at the throat, and we will drill a hole here in the wall of the pipe and attach a U-tube manometer. And use a manometer liquid which is different from the fluid flowing through the tube. So, I will draw another figure and show you how to make the measurement. Now, you may have noticed the way I am drawing this figure, that the angle of divergence is smaller than the angle of convergence, and the reason for that will be explained when we talk about boundary layer theory and flow separation. So, right now what we will do is we will put a drill a hole at the throat. And connect the static pressure tap over here with this tap over here. Now, let me draw the streamlines of the flow for inviscid flow. We will have a central streamline, the flow pattern will be symmetric. Now, this wall is also a streamline. So, you will have streamlines like this. So, you can see that the upstream streamlines are straight lines which are parallel to the walls of the duct, and the streamlines are going to be curved over here. Now, we will explain the reason for why we have placed the tap over here. This static pressure tap should be at a point where the streamlines are straight lines. We should not place the static pressure at say a location over here, and here also the shape of the converging diverging section is such that the streamlines here at the throat are almost straight lines. So, this is your Venturi tube or Venturi meter. What we will do is we will apply Bernoulli's equation along the central streamline. Now, I will go along this this is the direction of gravity. So, this is the horizontal tube. I will draw the vertical lines at this point on this central streamline. I will call point 1, and this point I will call point 2. Now, we will know that P 1 plus half rho V 1 squared plus rho g z 1, if I take z to be vertical upwards, will be equal to P 2 plus half rho V 2 squared plus rho g z 2. Now, once again, as we have seen, z 1 is equal to z 2. So, these two terms will cancel out. So, you have here a relation between the pressure and velocity at point 1 and the pressure and velocity at point 2. Now, if it is an inviscid flow, we expect the velocity profile to be a uniform profile over at 1 and a uniform profile at 2. So, if you want me to draw it again, the velocity here, if I draw the velocity profile, you expect it to be a uniform profile, because it is an inviscid flow. If it is a viscous flow, you will see the velocity will be brought to rest at the wall. So, you will have a boundary layer. Okay. Now, if you look at the velocity at this throat section, that will be uniform, but it will have a larger value because the area is smaller. Okay. Now, if you look at this section over here, say 1, and this or let me call it section A, and I call this the section T for the throat. Okay. You know that for incompressible flow, the same volume flow rate has to flow through the tube. So, Q A, if I say Q is a volume flow rate, is Q T is what you will call Q, but Q A you can say is A 1 V 1, if this velocity is V 1 and this area is A 1, and Q T will be, if I call that A 2 and this velocity I say is V 2. So, this will be equal to Q. Now, this is what you want to measure, or you want to find this value using this device. So, if you know either V 1 or V 2, you can find Q, because A 1 and A 2 will be known. Now, let us go back to this figure which we drew. From here you can see that V 1 V 2 are linked through this equation, and if you want, say, I can rewrite this equation as half rho V 2 squared minus V 1 squared is equal to P 1 minus P 2. All I have done is taken this term and brought it to the right hand side of the equation, and this I have term P 2 I have brought to the left hand side of the equation. Now, this P 1 minus P 2 you can measure using this manometer. So, if this is known, you have a relation relating two unknowns V 2 and V 1. Now, what we have a relation between V 1 and V 2, which is the continuity equation which I have written over here. So, this is the equation for global conservation of mass. Or it is also commonly called the continuity equation. Now, the geometry of this venturimeter is known. So, you know what is A 1, you know what is A 2. So, you know the relation between A 1 and A 2, and in fact, if you want, from here you can say that V 1 is Q by A 1 and V 2 is the same Q by A 2. So, I can link both V 1 and V 2 to the unknown Q through this known areas A 1 A 2, and this I can substitute into this equation. So, here I can write this as half rho Q squared into 1 upon A 2 squared minus 1 upon A 1 squared, where I have used the fact that V 2 is Q upon A 2 and V 1 is Q upon A 1, and that Q being the same I have factored it out, and you have squares here. So, you have Q squared here. So, if you know what is A 1 A 2 and if you can measure this pressure difference P 1 minus P 2, then you have an expression which you can use to calculate what is the volume flow rate. So, here if I draw the manometer levels, you will see that this will be lower than this. So, this will be your manometer deflection H m. So, physically what is happening is, as the incompressible fluid is flowing through this duct from 1 to 2, the area is decreasing. So, the velocity is increasing because the flow rate is the same, and when the velocity increases, the kinetic energy is increasing and the pressure is falling, because the sum of pressure and the kinetic energy is constant, this being an inviscid flow. So, the pressure at 2 is less than the pressure at 1, and so this liquid level goes up. Okay. Now, I can show that this P 1 minus P 2 again is rho m minus rho into G H m. So, that will show again. So, density of this liquid in the manometer, once again we are denoting by rho m, and the density of the fluid flowing through the pipe and the venturimeter is rho, both are constants. Now, what we wanted was the difference in pressure along the horizontal streamline, which is the center line of the pipe, and this point, if I extend this line vertically upwards, is what we call 1, and this point, if I extend vertically upwards, is what we will call 2. Okay. Now, if you look at the streamlines at section 1, they are straight lines. So, you can apply the hydrostatic formula in the vertical direction, and similarly here also the streamlines are going to be parallel. but in between we have a curvature of the streamlines. Now, let us consider a point here. You can call this point 3, and this point you can call 4, and this point you can call 5. So, you have z, a horizontal line. This is your z equal to 0 or datum. We are measuring z as a vertical coordinate upwards, and the gravity vector is in the minus z direction. This deflection we are calling h m, and this length, this distance we can call L. Now, we will start with the fact that P 5 equal to P 4. So, P 5 equal to P 4. The reason being that 5 and 4 are at the same horizontal level, and they are connected by a mass of fluid of the same density, which is at rest. So, that mass of fluid is a manometer liquid. Now, P 5 I can write as P 1 plus rho g into this height between the level difference between 0.1 and 0.5, which is the sum of L and H m. L and H m. So, this will be equal to P 4. Now, P 4 is P 3 plus rho m g H m, because this column of liquid is at rest. Now, P 3 I can write as P 2 plus rho g L, and you have this rho m g H m. Now, you look at this and these two equations, you will find that the rho g L term here appears in both the equations. So, that will cancel out, and if you want P 1 minus P 2, that will be equal to rho m minus rho into g into H m. So, if you measure H m in the lab, and if you know what are the densities of the fluid which is flowing through the tube, this pipe or duct which you want to measure, and what is the density of the manometer liquid, and if you know what is the gravitational acceleration, you can predict what is the pressure difference P 1 minus P 2. Now, you can go back and look at this expression which you have derived over here. P 1 minus P 2 equal to this. So, this expression I will write again. We had shown earlier that P 1 minus P 2 is half rho q squared 1 by A 2 squared minus 1 by A 1 square. So, A 2 is the minimum area, or the area at the throat of the venturimeter. You can call it the throat area, and this A 1 is the area of the duct through which the fluid is flowing. Now, P 1 minus P 2 we have shown is rho m minus rho g H m. So, this is equal to half rho q squared 1 by A 2 squared minus 1 by A 1 squared. So, from this you get q squared is equal to twice g H m rho m by rho minus 1. What I have done is I multiplied both sides of the equation by 2 upon rho, and I moved this rho inside here, and this is divided by 1 by A 2 squared minus 1 by A 1 squared. So, which I can write further as 2 g H m rho m by rho minus 1, and this I can write as A 1 squared minus A 2 squared by A 1 squared A 2 squared. Now, the geometry is known, so this denominator can be found. So, by measuring this HM, you have an expression for q square, and if you take the square root of the both sides, you will get what is q. So, to summarize, let us see what are the principles we have used to find this. One is we have used the Bernoulli's equation here, but that gave you a relation between the pressure drop P 1 minus P 2 and two unknowns V 1 and V 2. So, we use the continuity equation in global form or the global conservation of mass to link V 1 and V 2 to get the second relation between V 1 and V 2. And then we have used the fact that the pressure distribution in the vertical direction here is given by the hydrostatic formula, although the fluid is flowing, the reason being the streamlines are straight. So, that also gives you a practical that tells you where to put the pressure tap. If you put the pressure tap say somewhere here where the streamlines are curved, then you cannot use the hydrostatic formula to find the difference in pressure between P 1 points 1 and 2. So, it is already 1 o'clock past 1. So, we will take a break for 1 hour and then we will start after the lunch break. Orifice meter ta bole dite. All right, since we had a interruption due to the network problem, we will continue for another 5 minutes or so. So, let us look at the principle of a orifice meter. So, here what you have is a sudden contraction in the duct. You have what is called an orifice plate, so if it is a circular duct, then I should show the center line. So, this is what you call the orifice plate. It is a circular plate with a circular hole at the center. Now, if you look at the inviscid flow pattern, streamline pattern, you will see that the flow will be symmetric about this line. So, this center line will be a streamline, and the streamlines will curve upwards and flow like this. Now, of course, if it is a viscous flow, then the fluid will separate and you may have vortices here and here. So, here what we do is we will put a static pressure tap slightly upstream and a static pressure tap downstream and measure the pressure between these 2 points by connecting a flexible tube as before, as in the case of the orifice meter, and using a manometer liquid. Now, we will look at the flow pattern in a little more detail. So, we will consider a sharp edged orifice over here, okay, and this is the direction of the flow. So, if you look at the streamline here, you will see that it will go like this. So, the fluid which is on the left hand side will flow through this orifice, it will issue like a jet and the jet area will contract and then again it will increase. So, this minimum point here is called vena contractor. Now, what you can do is put a static pressure tap at the vena contractor and a static pressure tap upstream. Now, you may have a flow which is recirculating here. So, these streamlines may be curved, but if you look at what is happening along this line, these streamlines are almost horizontal lines. And you will have a similar view over here. So, this is an exaggerated view of what is happening. Now, if the streamlines are almost horizontal lines over here, then you can apply the hydrostatic formula between when you want to find the pressure difference in this and a point inside the manometer tube. So, you would like to connect the pressure tap here also at a point where the streamlines are almost horizontal. So, you may have a recirculating zone over here also. So, eventually what you will find is that you will come up with an expression which is very similar to what we have obtained for the venturimeter. Now, you have to understand one thing, that we are applying Bernoulli's equation, which is only for a inviscid flow, whereas in reality you have a viscous flow. So, you can define what is called coefficient of discharge. You can call it C with a subscript small d for discharge, which is the actual flow rate by what we can call the theoretical flow rate obtained by assuming that Bernoulli's equation holds. So, the expression which we have derived is will give you Q theoretical, and you will find in practice that this is going to be actually less than 1. Now, this coefficient of discharge can be found by doing experiments in the lab, and you can show that for a given geometry it is a function of the Reynolds number of the fluid flow. So, if you had a truly inviscid fluid, this ratio would be 1, but all fluids are viscous fluids. There is no fluid with a viscosity 0. So, in practice, to get the Q actual, you have to use this C d and multiply this expression for the theoretical flow rate by this C d. Now, you will find that C d for a venturimeter is larger than the C d for a orifice flow, orifice meter. The C d value will, as I said, would be 1 for inviscid flow. Now, in an orifice meter, because of the sudden change in the area, you have this recirculating flows or eddies or whatever you call it, flow separation, and the viscous losses are more. So, C d is going to be lower than the C d for a venturimeter. Now, I have discussed the principle of an inclined manometer 2 days ago, and there I had mentioned that whenever you make a measurement, there is an uncertainty associated with it, which is of the order of the least count of the instrument. Now, here what you are measuring is the manometer deflection HM using a linear scale, and once again the uncertainty will be the least count of the scale, which may be of the order of 1 millimeter, and the relative error is going to be small when HM is large. So, you have an uncertainty in the measurement which is delta H by HM. So, this will be of the order of 1 millimeter. So, the larger the value of HM, the less will be your relative error in the measurement, and you can find how errors propagate into the calculated value, and you can estimate what is the uncertainty in the value of Q, which you calculate using this formula. Now, if you have say flow of air at low Mach numbers, that can be treated as an incompressible flow, and you can apply Bernoulli's equation to it. Now, should you use a Venturi meter or should you use an orifice meter for that case? Well, for flow of air, where the density is small, the HM, if you use a Venturi meter, is going to be small. For the same pressure drop, if you use an orifice meter, the HM is going to be larger. So, for flow of air through a tube at low speeds, if you want to find the flow rate, you would prefer to use an orifice meter, because for that HM is going to be larger and the relative error is going to be less. On the other hand, if you have flow of water, let us say through a pipe, you may use a Venturi meter, because there anyway your HM is going to be large. Now, to find CD, you have to do calibration experiments where you measure HM, the manometer deflection, and find out what is Q theoretical through the formula which you have derived, and the Q actually you have to find by collecting the water, let us say if it is flow of water in a beaker or measuring flask, time it and find what is the actual flow rate, and you can repeat the experiment for different Reynolds numbers and find how CD varies with RE. Now, one fact helps you in the measurement is that if RE is large, typically turbulent flows, then CD becomes a constant roughly, which is independent of the Reynolds number. So, if you know what is the value of the constant through your calibration experiments, then you can simply multiply this Q theoretical by that constant value and get the Q actual. On the other hand, if the Reynolds number is not too large, then CD will be a function of RE, and RE will depend on the flow rate. So, although you have one equation where it is a nonlinear equation, and you may need to use iterations to find out what is the Q actual. So, with this I will stop.